Thank you. So let's try. What we will do now is we will play the battleship game, Морской бой. That's one battleship. That's the outer boundary of it. It's inside. That's the other one. It's either of these two. I'm not telling you which one, but it's one of them. So you make a try. This is point A. I say you hit it, then you know it's the blue one. I say you didn't hit it, then you know it's the black one. What if you try point B? I say you hit it, doesn't give you any information. Could be either of them. What about point C? I say you didn't hit it, but doesn't give you any information at all. So how can we phrase that point A is different from both B and C? What I will do is think of these individual battleships as a family of sets and restrict every single of these sets on this one-point set. Or a one-point set. Now in this case, if you think of this family of two sets and their restrictions, it gives you two sets. The full one-point set and the empty set. Here and here, it gives you only one set. The full set or the empty set, both times. So here you can distinguish, it gives you two sets. It's a lot. Here, not that much. So let's think about the cardinality of it. Cardinality means the number of points. It's not the Cantor thing, just the number of points. Okay? So for example, if this cardinality equals the cardinality of F for some finite set R, then you are fine. This set R is enough to figure out which set I have in mind. I don't have to take care of all points. I just need to find some set R that does the job. So for example, if I'm given the chance of checking some n points, I would like to try to maximize this quantity. So maximize over all finite sets which have exactly n points to maximize this quantity. Of course, maximizing it is good, but once you maximize it, among the sets that maximize it, you can choose. For example, you don't want to have a situation when you restrict to some combination and there are many, many pre-images corresponding to that. So just knowing that some combination of endpoints gives you less information. So you want kind of this restriction operator be so that every restriction has not very many pre-images. You want them to be balanced. But still, if you think of this quantity depends on n and on the family. So I denote it by tau n of f. It's a numerical sequence that somehow describes this family. I was talking about a finite family, but f could be an infinite one too, because this is always finite. It's bounded by 2 to the r, the number of subsets that an n-element set has. So this is always some sequence of numbers that somehow grows. If f is finite, it just gets stuck at some point. If it is not, then it keeps growing. So this function was called quite unimaginatively as a growth function. So this growth function, it doesn't depend on some metric or some probability or something like that. It's a purely set theoretical notion. You don't need this family F to be on a square. It's just some sets, and it describes how these sets in F overlay with each other. Are they pairwise disjoint? Are they too much stuck? Or when they are stuck, in which way they interrelate with each other? That's one of the notions of describing it. the way they interlace with each other, the family F. Okay? So this is called the growth function, and it answers for this interrelation thing. It's the first thing you would think in kind of strategy, but this has some other applications too. So let's think about this problem from the other side. Okay? And from the other side, I mean more or less literally. I will try. Yes? So I'm simplifying the problem. Instead of trying to find some kind of strategy by knowing F in advance, I take no strategy. I take these attempts to be random, uniformly distributed, independent. Uniformly distributed, independent tries. Now, once we talked about all these things, seems like the most unconventional thing to do. But it does make sense. For example, if you are in a store, every item in a store has a QR code. You want to scan them and learn which item you mean. So the number of QR codes is not very big. And these QR codes are somehow uniform, you can see. So if you don't know anything about all these QR codes, how they are distributed and so on, the first thing you would do is take random endpoints and try to figure out which QR code from the few QR codes in the store you meant. So this is a simpler thing, but it's not an oversimplification. It's like of your first attempt. Take n random points, try to learn which set out of the few sets that you had in mind you want. Now I simplify it more. I'm only asking you to learn how many of the black dots are there in the QR code. You check only n points, not every single point. You want to learn the probability of that set, the measure. How many black points do you have? So you want to learn it. That's the word, learn. Learning theory, machine learning comes from here. So this just one kind of the simplest characteristics of that set. You want to figure it out. The things that you do is Bernoulli's theorem, that you form the empirical distribution, that is n attempts, you check how many of those attempts were successful, you divide it by the total number of attempts, n, and this will be an approximation for the measure of that set, if the measure of the whole space is 1. So d sub na minus pa. Okay? So I take kind of the first theorem out of the probability theory, called Bernoulli's theorem, say, it takes that this goes to 0 as n goes to infinity. So for every positive epsilon and for every measurable set A, if you take uniformly distributed independent random points, then this goes to 0 in probability. That's Bernoulli's theorem. Bernoulli's theorem works for every single set A. My question is, if you know in advance that it's not some measurable set A, that instead it's from the family, and you know the family in advance, could you say something more? So see what happens. Once we see Bernoulli's theorem, we develop from here towards probability theory. In the sense that we think, what if we think not in terms of this convergence in measure, or in probability, as probabilists will say, but like almost everywhere convergence? What if you think about these animals not independent, but you allow some covariance? What if you think about them tail estimates, right? All this story. But there you have a set A, which is measurable, and that's it. It should work for every set A. But what if we go this direction? We have a family of sets, and you want to guarantee that this convergence to 0, so I write supremum here, A in family, is uniform. I mean, if the family F is finite, it's uniform. Could there be families which are infinite and for whom this convergence is still uniform. So that by knowing it at n points, you can tell that it is close to PA in some sense, no matter which A you take. I mean, generally speaking, if you take a probability space rich enough, you can just come up with examples when it's just not uniform, just some small sets here or big sets, you know. But could it be uniform? Could you guarantee that if you scan at n points, then you are close to the number of black points uniformly, no matter which item you bought in the store? So that's the way it goes towards the learning theory. Uniformity, not like the finer details of convergence, but uniformity of convergence of these things. So this is the thing here. F as a family is given. A varies in the family. D and A is always about uniformly distributed independent things. And this family is now in some kind of probability space. It wasn't, but it is. So one would anticipate to have an estimate on that, which has two factors. One factor is a Bernoulli type factor, which depends on epsilon and goes to 0 as n goes to infinity. And separate from it, there's another factor that answers for this property of the family F. So this is what the theory of Vapnik-Chervonenkis is about. They have the whole theory. It's one of the basic theories in machine learning. They have this thick book, but where this all happens in their very first article in 1971, published in this Russian journal Theory of Probability. And everything is there in this very short article. All their constructions. So everything I was telling so far is just an excerpt from their article. And the thing is, they could prove it. They could prove that this could be estimated from above by a product of two factors. I'll use a different color. This factor and this factor. One is going down to 0 exponentially, like you would expect in Bernoulli's theorem. There is the epsilon animal, the n animal, and the other factor, so this is a multiplication, is the growth function of the family. So the growth function of that family, a purely set theoretical property, which has no probability, and it relates to these interrelations, controls the way this is estimated. And as you can see, so the Bernoulli factor is going down exponentially fast. So what you want from this growth function is not to grow faster than exponential. Sub-exponential works well. So if this overlay type of things, this growth function, grows sub-exponentially, then you have the uniformity. Moreover, you quantify how fast it goes to infinity. And they have, what is amazing is that they have this condition in terms of being necessary and sufficient. Sub-exponential growth for the growth function is necessary and sufficient condition for uniformity of this, for this uniform estimate to hold, for this to go to 0. It's just a property of these interrelations. And these sets, you just imagine them as Venn diagrams. So by a closer observation of their proof, I could just improve it a little bit to find a tighter estimate both for the exponent and for the growth function. So that's the result. In fact, a tighter estimate holds. Now, if you think about this theory, this is some kind of abstract theory. In particular cases, you would want to evaluate this growth function. And let me speculate of how this is done and what this is related to. So the growth function answers for how much they overlap And if you want the growth function to be big, you would want them to be kind of separated out, these sets. Not like stuck one on the other, but separate out. This will guarantee something. And the way you could separate out, you could say that individual elements there have some kind of distance, for example. So you would want to construct sets when there are elements which have quite a big distance. And that's covering numbers. And that relates to entropy theory. And this is something that you could see in the machine learning thing. Another way is if these are families of functions, then if you want to guarantee distance between functions, for example, you expand functions in some kind of orthogonal series. You look at these coefficients, and you want to guarantee if these coefficients are different from each other, then the functions are different from each other, so there's not many overlays. But guaranteeing that if the coefficients are different from each other in this orthogonal expansion, then the functions are different from each other, it relates to Rademacher complexity. So in a way, entropy, covering numbers, Rademacher complexity, and this growth function, they are all somehow interrelated, but not in trivial ways. It's not that one estimate implies the other estimate. There are all kind of non-trivial estimates that happen when you go and dig deeper in that theory. But what I really wanted you to show is the statement of this theory. What do these people really want? They want uniformity with respect to a family. That's it.